Good morning, everybody, and welcome to Physics 101. Today is Wednesday, October 26. We are in the second part of week 8. We are dealing with electricity today. I know some of the concepts that we're going to be discussing today were introduced in the lab on Monday. So we're going to build on those concepts basically and try to define some other things, like, for example, the electric field, which we did not introduce on Monday, but we're going to revisit Coulomb's law and try to understand basically a little bit of its historical context and what it means. And also we are going to compare it to gravitational universal law of gravitation of Mr. Newton, basically between masses. And also note, very important note in here when we're talking about electricity, Chapter 20, which is the topic of today, is not included in this exam 2 that is scheduled for next week, basically. Or is it? No, it's Wednesday, November 9th. So it's not next week, it's the week after, actually. So that's the plan for this chapter. So next week we'll be covering more chapters from electricity and magnetism. We'll get into a little bit of circuits. And then the week after, of course, we have the exam. There were a few things that were posted yesterday actually on Canvas, namely the problems that you guys are supposed to be also reviewing for the exam, because this exam will have a component of it that is actually problem solving. So at this point, you're going to have 3 problems. So it's already decided. So you're going to have 3 problems. And the 3 problems, they amount to 25% of your overall grade for exam 2. So exam 2 will be component conceptual, which is 75% of your grade and 25% coming from the 3 problems that you're going to be doing. So I strongly urge you guys to go through all of those problems that we did on Monday, October 10th. And then a couple of them also, we did them on October 17th. And make sure you fully understand how those problems work, so that when you come exam time, when you're doing the problem section of this exam, that you are fully confident, basically, and you just approach them and you start hammering the numbers and make sure you understand what you're doing. Not 2 exams will be alike, so that you guys know. So it's going to be online. Both the conceptual version and also the problem session are going to be both online, and most likely the written version of the exam is going to be the 10th, which is the Monday. Which is the Friday after the conceptual exam. So we'll have one day to do the conceptual, and the next day to do the written version of the exam. So this is basically how it's planned, and this is how it's going to be working. And I hope that you guys are ready, and you have enough materials to make sure that you guys are ready. Also, the conceptual, so it should be available today at noon. Basically, for you guys after this class, basically it's going to be available for you guys to start doing your reviewing. And it's plenty of time. You have probably about 2 weeks to go through the review. Granted, you have other classes and other things that you do, but this is good enough time for you guys to prepare for it and maximize your grade. Hopefully you score 100% in both versions. So this is in terms of the exam. The exam covers only chapters 2 through 7, meaning from it's all mechanics, basically. There is no electricity in it. And that's in a nutshell about the exams. That's basically what we did, okay? So without further ado, let me introduce the concepts that we discovered in the exam. And I know I did a demo actually in lab. And actually we didn't do it a demo, it's part of a lab. I'm trying to grab a piece of paper in here, okay? Anyway, I grabbed it. Oops, it fell back again. There it is. It's on my finger and it fell again. So I'm trying to grab this one now with a pen. This is actually a demo that is a typical demo for static electricity. And I'm sure you experienced this one in your lives. So, oops, I grabbed it, but then it fell. And here it is, okay? And now it fell again. So basically what's going on in here is that we're dealing with charges. That's really the point in here that you need to remember. And that's what electricity is. Electricity is a game that is played only with charges. If you have a charge, you can play a game. If you don't have a charge, you don't play this game. So again, the book sometimes delves into this philosophical debates and try to understand what is the meaning of this and that. And sometimes it really takes you into a kind of a rabbit hole, basically, that you will never be able to get out of, because that is not what physics is. Physics is a lot simpler than that. You absorb something, and electricity was something that existed with us as humans ever since we basically evolved. And we look at lightning, for example. That is actually discharge. I know in the ancients, probably they associated with magic and probably sorcery or some sort of a kind of a religious things and things like that. But that's what it is. It's an electric discharge. Then people, and one of you guys mentioned in the lab, actually, that the lab we were doing, where we were basically building charges using the tapes and things like that, that it sounded too simple. I mean, this is something he said, and it's literally basically what he said. This is probably something that we should have done in elementary school. And that is true. It is simple. But believe it or not, this is exactly what people have done in the 1600s and 1700s when they were trying to understand what electricity is. So do not cheat yourself. Just because it sounds simple, it doesn't mean that it is something little. It is really a big deal. Because here is what the time of Mr. Coulomb basically was going on at that time. People were playing with static electricity, and they noted this phenomenon. They noted exactly what we were debating in the lab, that if you make like charges, they seem to repel. Okay. They didn't know what they were, but if you somehow make something in here, they repel. But if you build them in such a way, remember how we did the unlike charges, we had those two tapes on top of one another, neutralize them, and then when you separate them, one of them ultimately is going to be a charge, the other one is going to be opposite to it. Case in point, if we bring them closer, they will attract one another. But if I make them in the same fashion, both of them, and I bring them closer, they will repel one another. So that's a phenomenon that was known there. And it took a long time, actually, a lot of people working on it, on those simple ideas, on those simple, basically, observations, that one of you guys noted that this is something that probably we should have done in elementary school, and that's true. But it took a long time and very smart people working on these same things to come up with some sort of a law. And that is Mr. Coulomb, who actually summarized all of these people's work and put it in a law. He didn't call it Coulomb's law. It would have been really something of a bad taste if you wish to discover something and you tell people, hey, I discovered it, so it has to be called after me. No. Of course, you discover something and hope that people will name it after you. And that's exactly what happened with Mr. Coulomb. So he basically summarized what other people have done, playing with charges, making half of the charge, seeing that the force drops by half, doubling the force, seeing that doubling the charge, I'm sorry, seeing that the force doubles, putting them this much apart to make them further away, and then the force drops like 1 over the square of the distance, bringing them closer, and the force increases by the square of the distance, or the inverse of the square of the distance, I should say. So in order to make things work, at the end, he needed to throw in a constant. So at the end of the day, this is what the law looked like. Let me share. And let me, first of all, let me prepare the notes because it's from another class. Let me get into here. Good. So let me go back where I was and share. And now I can share my notes. Okay, so basically here is the Coulomb's law at the end on how it's basically put. So we have the force equals to a constant. And I will tell you what this constant is for, times the first charge and the second charge divided by the distance squared. So the distance squared, I'm going to use r. So think about it this way, okay? You have a charge in here. Without really getting into the philosophy, what a charge is, what it means, and things like that, it's a charge. And I'm going to label it as Q1. Let's say it's 5 coulombs, or 10 coulombs, or 2.3 coulombs, or half a coulomb, or 1.2 microcoulombs. Okay, micro here is 10 to the negative 6. That's what the micro stands for, which is typical number for charges, by the way. A nanocoulomb is 10 to the negative 9. So you could have a nano, you could have a micro, and you could have a pico. So it's not common to find 5 coulombs or 2 coulombs or 3 coulombs, because a coulomb is a big charge, okay? So a pico is 10 to the negative 12. So this is the typical numbers that you deal with in electronics. So typical numbers is a microcoulomb, and that's a big charge, by the way, or a nanocoulomb, which is more of a typical number, sometimes even a picocoulomb, which is a very tiny number, 10 to the negative 12 coulombs. So those are the typical numbers that we deal with. But a full coulomb, no. So again, it was named after Mr. Coulomb, the charge, in honor of his work again. Okay, so that's basically in a nutshell what this is. So we have a charge Q1, okay? And we have another charge in here, which we're going to label it Q2. It's a similar, it may or may not be the same value, so this is Q2, okay? And they are sitting at a distance away from each other, which I'm going to call it R. So this is the separation between the two charges. That's basically what this is. If I bring them closer, the force increases. If they move them apart, the force decreases. If I double the charge Q2 in here, the force doubles. If I double the charge Q1 and keep Q2 the same, then the force doubles. If I halve this charge, the force halves, and so on and so forth. So that's basically what this law is. That's exactly what he did. That's exactly what a lot of people did, because after he came up with it, he had to check it. Now, the peculiarity of this force is that it could be repulsive or it could be attractive. So it's not always has the same direction, depending on the relative signs of these two charges. If Q1 and Q2 have the same charge, have the same sign, the same sign, meaning both of them either are positive or both of them are negative, okay? So in this case, the force is repulsive. F is repulsive, meaning they will repel each other. If Q1 and Q2 have different signs, meaning one of them is positive, the other one is negative, or one of them is negative, the other one is positive, then in this case, the force is attractive. This is unlike gravity. Gravity was always attractive. If I have two masses, so let me draw the similarity with masses. So I have a mass in here, M1, and if I have a mass in here, M2, and I put them next to one another at a distance R, this force is always, gravity is always attractive. So this is a big distinction between the two forces. This one could be repulsive or attractive. This one is always attractive. This one also drops like 1 over distance squared. This one also, if you double the distance, the force drops by a factor of 4. If you half the distance, the force quadruples. This is the same thing with the R. If you double the R, the distance between them, in this case, the force is going to be 1/4 of what it was originally. If you half the distance, meaning that you bring them halfway from what they were before, the force quadruple. So this is true for both of them. For the distance, it's the same effect. This also goes with the mass. If you double that mass, the force doubles. if you double this one and maintain the first one, also the force doubles. If you halve one of the masses, it's going to be halved too. So, and this one also goes with the charges now. So what is really a charge? It's just something I can measure in the lab. Don't make too much of it. Okay. Don't spend too much out of it. As a matter of fact, it's still a mystery at this point. So if somebody really wants to go them trying to understand where it really arises from, you really have to go through super advanced physics. And at that point, it's still something that comes from complicated symmetries and one of the most advanced theories in physics to really try to understand where it arises from. Same thing with the concept of mass too. It's as complicated and as mysterious as the charge if you want to really start to get into those details. But it's a property. For us right now, all we say in this case, a charge is a property of elementary particles. What I mean is particles. Okay. What I mean by it is, I mean, a particle, for example, you meet somebody has a name, okay? So every person has a name, they have a height, they have a weight, they have all kinds of, these are properties. So it's an intrinsic property of matter, that's it. It's something that they have it. So either a particle has it or doesn't have it. So let's take the three main particles that we talk about usually on a daily basis. So the first one is the electron. The electron has a charge which is equal to, the symbol for the elementary charge of the electron is E. And E stands for 1.6, so it's negative 1.602 times 10 to the negative 19 coulombs. So that's it. This is a 9, by the way. I know some of you in the lab were kind of wondering what is that? Is that a G or a 9? So it's a number 9. But my 9 and G look alike. Anyway, so, and actually the Q also now looks like to them too. So I'm sorry about this. That's my handwriting. I'm sorry about that. So the second elementary particle that we're going to mention in here is the proton. So that you guys remember, if you have ever taken chemistry, is that the nucleus has protons and neutrons in it. So this is the inside the nucleus. Some of them are protons, some of them are neutrons. Which one is which? It doesn't matter at this point. And then in the cloud above the nucleus, there are electrons. So this is the electrons. Inside the nucleus, there are protons and neutrons. And as the name suggests, the proton actually has a historical name why it was called proton, because was it Rutherford or who thought that it's really the most elementary particle there is. So again, the proton has a charge Q, which is actually a positive, the same value in here. So it's a positive 1.602 times 10 to the negative 19 again coulomb. The third particle does not have a charge. So neutron has a charge that is exactly 0. So that's basically what that is. So that's really the fundamental property of what the charge is. Some particles have it, some other particles have it. Now, on the macroscopic level, on the big level, like for example, when I did the pen earlier, it has atoms. It has a bunch of those atoms in here. And at the end, it's the net charge that is either been withdrawn from the material. So in this case, it's going to leave it positive. The number of electrons that were taken out, okay, or the number of electrons that were dumped into the material. So if you think about it, let's take, for example, two kinds of materials in here. So think of this as whatever it is, a blob of material, okay, so it's something. And another one in here. So for a process, for example, I could go and manually take an electron from here and put it in here. So this one will become negatively charged, and this one will become a positively charged. So I took an electron and I moved it from one material to the next. I'm going to do the same process again. So I'm going to take another electron in here and leave a vacancy behind it and dump it in here. So again, another electron in here. So, and now I have a negative charge in here, but I'm left with a positive charge in here. That vacancy is because, remember, a neutral atom has an equal number of protons and neutrons. So if I take an electron out, then in this case, I'm leaving positive net charge because it was balanced before I removed the electron. Now it's not balanced anymore. So now I lost an electron. If I continue doing this process again and again and again, many times, okay, so at the end, I'm going to end up with a net negative charges in here and a net positive charge, which must be equal. So I have to be careful here. I have 7. So I have 4, 5, 6, 7 charges in here. So in this case, basically what I did was I took 7 electrons. So if you ask me how much the charge of this, so this one is a negative 7 times that 1.602 times 10 to the negative 19 coulombs. If you ask me what is the charge of this one, it's easy. It's a positive 7 times 1.602 times 10 to the negative 19 coulombs. So that's basically what happened in this scenario. The point I'm trying to say also here is that any given charge, any charge Q, is an integer. In this case, it's 7. In the example I did, an integer, meaning given number. It's either positive or negative. In this case, it's negative 7, and in this case, it's a positive 7. If you're not familiar with the number system, I mean, there are the natural numbers. They start from 0, 1, 2, and so on and so forth, and 3. But then there are the integer numbers that extend the natural numbers to a negative number, negative 1, negative 2. So that's basically what that is. So an integer, which is positive or negative, a whole number. That's what that is. An integer multiple of 1.602 times 10 to the negative 9 coulomb. That's it. Obviously, this number can be ridiculously high on a macroscopic scale, on a big scale, that is. So if you see a chart, technically you could count how many electrons or protons basically at the end that charge amounts to, okay? But it's too big. So the mere fact that it's an integer multiple doesn't mean that at the end I'm going to count it like 3,316,000,000, whatever that is, okay? So at the end of the day, I'm going to treat it as a continuous flow of charge. On a macroscopic scale, it's treated as on a macroscopic scale, meaning on a big scale, that macroscopic versus microscopic. On the macroscopic scale, the charge appears continuous. I mean, the analogy with that is simple. If you go to the faucet right now and turn on the water, you will see a continuous flow of water. So you can treat that flow of water as a continuous fluid. I mean, if you have a hose, for example, and you run the water through it, it's going to shoot one particle after another as if it's a stream that is continuous of water. But you and I know that this is not true. If you look at the water on a microscopic level, it's made up of individual molecules of H2O. So each particle is actually 2 hydrogen atoms attached to an oxygen atom, forming H2O. So you and I on microscopic level know that this picture is not correct, that the flow of water is actually discontinuous, discrete number of particles that one follow the other. But because when you turn on the faucet, you don't see that, you see just a continuous flow, that is the similarity in this case too, that you will see the charge flowing as if it's just one full thing, one stream of basically one line that is continuous, because it's too many of them. Same thing with the flow of water. So this is basically the picture that we want to convey in this case. Furthermore, the charge is conserved quantity. In this case, if a charge disappears from here, it must appear somewhere else, okay? So charge is conserved quantity, at least on the local region. Charge is conserved quantity. Just like when we did the energy and we said the energy is a conserved quantity from chapter 7, and everything, charge is too. So these are some of the properties that of charges. This one is important actually when we do electricity later on, trying to understand the flow of current and how charges move from place to place. We have to come up to this understanding. Now, a word about the units. I know I mentioned the fact that it was named after Mr. Coulomb, in honor of Mr. Coulomb, but it's really not a fundamental unit. The unit of charge is the Coulomb, which is, what is a Coulomb? Which is the amount of current that is okay, the amount of one ampere of current. So we really need to define it correctly. Ampere, let me write the ampere correctly. 1 ampere. This is the symbol for the ampere is capital A of current that is collected in 1 second. Okay, we have defined something with something else. You're asking, okay, what is the ampere then? Well, the ampere is part of the fundamental units of measurements, okay? Remember the fundamental units so far are the meter, the kilogram, the second, and the ampere. The ampere is actually another fundamental unit. This is the unit for current, okay? So those are the fundamental units. So it's more appropriate then. So a coulomb, so 1 coulomb really is 1 ampere times 1 second, okay? So that's basically what that is. So now I have the ampere, which is a fundamental unit, and the second, which is a fundamental unit. And this is like the Newton. So remember when we said the Newton is not a fundamental unit, and the Newton was 1 kilogram times 1 meter divided by 1 second squared. That's basically what the Newton is. So Newton is not a fundamental unit. So is the joule, by the way. 1 joule was 1 Newton, which is not a fundamental unit by itself, times a meter, or 1 kilogram times a meter, that's 1 meter squared per 1 second squared. So those are the fundamental units, okay? So I know I defined something using the ampere, and then at the end, the ampere needed to be defined. And the ampere can be defined by measuring with an ammeter. So you bring an ammeter and you run current through it, okay? And you read the basically the reading on the ammeter. So if it reads 1 ampere, that's exactly what that is. It's 1 amp, okay? That's what the current is. So if there is a current flowing in here, that is 1 amp. Obviously, this is dumping charges at the rate of 1 ampere, 1 amp per second. So at the end of the day, how much charge you have collected in here? If you have collected 1 amp in 1 second, that means you have 1 coulomb, okay? That's in a sense what the definition is. I know it's kind of going in circles, but that's basically what, in terms of the fundamental units, is. So this is Coulomb's law so far. Okay. And Coulomb's law now needed some comparison with the, I know I compared it a little with the force of gravity, but we need to further compare it in here to have an understanding with it. So let's say, for example, I have an electron. Remember, the electron has a charge that is equal to negative 1.602 times 10 to the negative 19 coulombs. So this is the charge of the electron, which is negative. So I'm going to put the symbol E next to it in here. And it's equal to negative 1.602 times 10 to the negative 19. And let's say I have also a proton, and the proton in this case, the charge is the same thing, except that it's a positive number. And I put them, for example, next to one another. Let's put an electron in here, and let's put a proton, which is typically bigger, next to one another. Obviously, they will attract one another because these are opposite sides. So let's try to understand now how much force they attract one another. And the separation between them, it doesn't matter at this point. I'm going to put them at a distance, for example, of 1 meter. 1 meter is a big distance for these two tiny particles. Okay. So I make the calculation a little bit easier. I forgot to mention about the constant K in here, and it's actually in the book too. This constant K is just a constant that depends on the medium. So K in air or vacuum, it's equal to 9 times 10 to the power 9. The units for it are the units of the force in Newton times the units of distance, meter squared, divided by the distance, the Coulomb squared. Because if you put the Newton in here, it's going to cancel this Newton. The meter squared will cancel this meter squared, and the Coulomb in the denominator squared will cancel the Coulomb squared. So everything matches. So this is that constant, okay? So I'm interested trying to find how big the force of attraction between these two at a 1 meter distance away from each other. Well, the force in this case, due to electricity, is equal to a negative number because it's negative times positive, times 9 times 10 to the power 9. I'm not going to put the symbols right now, the units right now, times 1.602 squared because it's the same number, times 10 to the negative 19 squared also, divided by 1 meter squared, which is 1. Okay. When you're dealing with such a big numbers in here, the first thing, or powers basically, the first thing you have to handle are the powers. And the negative sign in here, so it's going to be in Newton because everything else cancels except at the end it's in Newton. So at the end, so the main thing I need to handle are the powers. So 1.6 squared is what? About 3 times 9, which is about 30. So I know 27 is about 30. So the whole thing is about 3 times 10 to the power something, 1, okay? So at the end, initially, so at least this square is in here, and this one will give me about 3. I mean, if you're curious trying to put this one in a calculator, go ahead and do so, times 10, because 30 is about 3, 33 times 10. But then I have 10 to the power 9, and I have 10 to the power negative 19 squared. That's 10 to the negative 38, because I have to multiply 19 by basically 2, which is 38. Okay. Then 10 to the negative 9 and 10 to the 10 to the power 1. So that's 10 to the power 10. And here I have 10 and I have negative 38. So it's roughly about 10 to the negative times 3, if you like. Okay. I'm just interested in how big it is on order. So I'm not really interested in the exact number. I'm just trying to see how big this force is between the two. So it's 10 to the power negative 28 Newton. So it's a very, very tiny force between the two of them. How about the gravity now? I need to know the masses of the two things. So the force of gravity now is, remember, G times the mass of the electron times the mass of the proton divided by the distance squared. The distance squared is going to be the same thing. And G is a negative, this whole thing has a negative sign in front of it. So it's an attractive force too. So they will attract each other too. So it's a negative 6.67 again, times 10 to the negative 11. That's what G is. 6.67 times 10 to the negative 11. The mass of the electron is 9.1 times 10 to the negative 31 kilogram. The mass of the proton is 1.67 times 10 to the negative 27. The whole thing is divided by 1 meter squared. 1 meter, the whole thing squared, okay? Because I'm putting them still, so I need the mass of the electron and I need the mass of the proton. The proton is about 2,000 times heavier than the electron, okay? But they're too tiny still. So here is the big deal in here. The force of gravity between these two, I'm going to get a rough number 2 in here. I have 9 times 6.67, which is roughly about 7. 9 times 7 is about 60 something. So I'm going to put it around 6 times 10 to the power 10, roughly. So I'm just interested in the order of magnitude. Times this 1.7, so it's going to be about 8 or 9, okay? So I'm going to put it around 100. So 1.67 times 9 times 6.67, and I'm going to put it roughly about 100, which is 10 to the power 2. Again, I'm not interested in the exact value. If you are, go ahead and punch it on the calculator, and it's not going to make much difference, honestly. So 10 to the negative 11 times, and here I have 10 to the negative 31 and 10 to the negative 27. So I have to add the two numbers. So I have to add 31 and 27. That is 58. 58 and 11. That is going to be 69. 69. Now I have to remove 2 of it. So it's going to be 10 to the power 67. So at the end, the force of gravity is going to be 2 minus 11 minus 58. So it's going to be 69, 67, 10 to the negative 67. The big deal in here is that although this force, according to the number that we calculated due to the electrostatic force, is a very, very tiny force, this is even ridiculously smaller. So let's see how big the force of electrostatic over the force of gravity. And I'm just doing the ratio here. I don't care about this number, honestly, because it doesn't make much difference. 3 times or less 3 times. So at the end of the day, it's this powers that are going to be important. So it's going to be 10 to the negative 28 divided by 10 to the power negative 67. And if I'm careful enough, this is about 40 or 39 to be more specific. Because at the end of the day, you take this one to the numerator, it becomes positive. So let me do it step by step. So I have a negative 28. And when I take the 67 to the numerator, it's going to be positive 67. So it's going to be 67 minus 28, which is 40 minus 1, which is 39. So it's ridiculously much stronger in terms of electricity between a proton and an electron than between their gravity. So it's 1 followed by 39 zeros. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 threes, that's 39. This is how big that is. This number, I cannot even read it. This is 1,000, million, trillion, billion, and then the number of trillion, whatever that numbers are. So the force of gravity, I wrote it already, is extremely, and this is an understatement, weak compared to the force of, to the electrostatic force. Electrostatic force. That is the bottom line. So basically, what dominates in here is electricity. It's ridiculously strong compared to gravity. Okay. Yet on the large scale, for example, on the galaxies and the stars and the planets and everything else, gravity dominates. So on the universe, gravity dominates. If you take things on large scale, gravity is the one that dominates. Yet it's extremely weak. I mean, beyond the belief, it's weak compared to electrostatic force. So why is that? Because most matter is neutral. Period. Otherwise, if matter is slightly charged, electrostatic force will dominate. Most matter is neutral. I mean, charges, they come in pairs, positive and negative, and they cancel. So the atom is neutral. That's why, for the most part, we don't see electricity flying every which way. Okay? That's why electricity is not really apparent everywhere. But on the atomic scale, electricity is dominant. For example, between the electron and proton, electricity plays a more important role than gravity. Both of them, they drop like 1 meter squared. So if you're wondering what happened if I put them closer than 1 meter squared, well, this number will increase, or at least the inverse will increase in this case, and so is this one, but the ratio stays the same because it will cancel anyway. Because when I do the ratio, when I did the division in here, whenever I'm dividing by in here and I'm dividing by in here, so the answer, the distance doesn't matter. So if I put them at 1 centimeter apart, so this force will become 100 times bigger, squared, that's 10,000 times bigger. And so is this one 10,000 bigger, but at the end, the ratio doesn't matter, it stays the same. Remember, 1 centimeter is 100th of a meter, but I have to square 100. So it's going to be 100 times 100th, which is a 1/10,000th, but it's in the denominator, so it's going to go upstairs, it becomes 10,000. So it's this one. But at the end, 10,000 and 10,000 will cancel. That's it, at the end of it. Okay. If you put them at a micrometer apart, which is probably a little bit more significant in this case, if you put them a micrometer and you square the micrometer, it's going to be 10 to the power 6 squared. That's 10 to the power 12. So it's going to be a trillion times more electrostatic. And so is going to be trillion times more gravity. But at the end, the ratio stays the same. If you put them at a nanometer, which is more the size of an atom, that slightly basically bigger than what a normal hydrogen atom is, then this number becomes 10 to the power 18 bigger. And so is this number, by the way, and the two cancel still. So at the end, the ratio stays the same. So on that level, this force becomes ridiculously strong, relatively speaking, because even at 10 to the power 18, it's still 10 to the negative 10 newtons. So it's a ridiculously small number. So it's a force, even at those distances, which is actually 10 to the negative 10. So it's still 10 to the negative 8 Newton. So it's a very tiny force, even on the actual scale of the atom. So there are other mechanisms involved in this case, other reasons for the atom to be involved. And these are not the entire picture, though. So the picture that emerged from this discussion is that the electrostatic force is a ridiculously small force. I mean, yes, but it is a very, very strong force compared to the force of gravity when it comes in. So that's basically the point I'm trying to make in here. And so this is in a nutshell what Coulomb's force is. This is how it's represented. So I have a positive charge in here. I'm going to put it a positive charge to make sure. And basically, if I bring another positive charge in here, that positive charge in here will be subject. So this is the positive charge in here. So this is going to be subject to a force that is going to repel that one. If I bring a negative charge in here, that charge is going to be attracted. So this is positive and this is negative toward the central charge in here. If I bring a charge that is exactly 0, that force is not going to be there, neither this way or not that. So that's really what the picture that emerged from this whole discussion. Now, all of this is interesting and it's good to know. There is another concept two concepts that I need to introduce before it's done. And those two concepts are the electric field and the electric potential. The book uses this symbol that kind of annoys me a lot. I have never seen it in my life at all. Electrical potential energy. I have never seen this symbol, by the way, in my life. And this is the first time I saw it in the book in here. So it's kind of, usually we call it potential energy, and that's the end of it. So it's due to electricity or due to magnetism or due to whatever potential energy is potential energy. In this case, it's going to be potential due to electricity, but they add an E in front of it. But the electric field now is an important concept that we need to understand. Going back to my analogy to begin with. So think of it, I have a charge Q sitting in here, okay? And it's a positive charge. So let's make it positive just to simplify life for ourselves. And let's say for the sake of argument, I'm bringing 1 Coulomb test charge. So I have 1 Coulomb test charge. So go to the store and tell them, you know what, I need a test charge. 1 Coulomb test charge. I don't want half a Coulomb. I don't want 5 Coulombs. I don't want 2.37 Coulombs. I want exactly 1 Coulomb test charge, okay? And bring that one and attach to a spring system, mass system. I don't find where my spring in here is. That measures forces, basically. It's a scaled spring that has how many newtons are going to be pulling on it. Choose for weights, and you choose for forces. So you attach to it, and then you bring it next to this Q charge. Put it in here, for example. So this is where your test 1 Coulomb charge is going to be. So it's a positive charge, by the way. Okay, so it's a test charge, and you put it at a certain distance. Obviously, and if you attach the spring this way, for example, attached to it, you will see that it's dragged. It's going to pull the spring in here, and it's going to pull it this way. Because this is positive, so it wants to move this way, away from it. And you know what? You say, what I'm going to do now, I'm going to bring it closer. So you're going to put it, so you're going to attach your spring system in here, and you're going to put the charge in here. So what you notice in this case is that the spring stretches so much. This is how it's going to go. And let's say for the sake of argument, you decide to put it further away on the other side in here. So if you wanted to put it in here. So what you notice in here is that the mass, the charge, which is still 1 Coulomb, by the way, still your test charge. You're just moving it around, that's all. It's going to be pushed, but not as much as the first 2 cases. So imagine with me that you do this throughout the entire space surrounding it. And I don't mean the 2-dimensional space, I mean the 3-dimensional space, the entire region surrounding this charge. This is a picture, and then you keep on drawing these arrows, draw an arrow, draw an arrow. So this is a picture that emerges after a while. So you have a charge, again, that is positive, Q. So if you go very close, the field is very long. The force is very long. If you move away, this is how much it is. If you move away, it's going to become smaller and smaller and so on and so forth. But at the end, you're going to have it everywhere. There's going to be a continuous line in that region. If you go this way, it's going to be a continuous line. If you are close by, the line is bigger. If you are further away, the line shrinks, but it's going to be the same line anyway. In here, if you are close by, if you put it nearby, the force is big, but it's pointing away. If you move further in here, for example, it's still pointing away, although the line is shrinking. But you're doing everywhere. So you're not missing a single point between the points. I know it's kind of hard to do, but this is we can imagine doing it, okay? Same thing in here. So what I'm drawing right now, this is everywhere in space in here. I'm drawing what is known as a field lines. Since this is positive charge, the test charge is being repelled by this test charge, by the charge in here. So how much force we're going to end up with? It's going to be K times 1. Remember, the test charge is 1 times Q, which is this charge in here. This is the source. So I'm going to put it source in here. Divided by how far we are from it, distance squared. Now, here is the trick. Let's say, well, you go and get another charge now, not the test charge, another charge, okay? And you put it now anywhere here, for example. So that's going to be easy since you already measured this quantity, which we're going to call the field now, E, the electric field E. Then you don't need to do anything. At this point, you can find the force by subbing the value of 1 coulomb by that charge you bring in here. So if you bring a Q charge now, not the source, another Q, then all you have to do is multiply it by this quantity because everything is in there. You have the K, you have the Q of the source divided by the distance squared, which is this distance, and you know that quantity in that point. So all you have to do is multiply it by this quantity, and that's it. And you have found, so I'm going to call this one, so this one is E. So I'm going to find the force now is easily. So this is E now. So E is subbing this value by 1, that's it. So it's going to be then Q times this value of E. So the electric field E then is simply the force divided by this Q. And the force is in Newton, so that you know the measurements for it. And the coulomb is the unit for the charge. So the electric field then, if this is 1, then E and F is equal to one another. Electric field is the force exerted on 1 coulomb test charge. Period. That's it. So if you don't have a 1 coulomb test charge, just multiply by that charge, and divide by that charge, and now you have the electric field. So the electric field is a force, really, but that force is for 1 coulomb. The unit for the electric field is Newton per coulomb. I know Newton is not a fundamental unit, but it's a derived unit, and the coulomb is not a fundamental unit, but a derived unit. But the combination of both of them is going to be the unit now of the electric field. So this is in a nutshell what the electric field is. So if you have a positive charge, all the field lines are coming off of it. And this is not all the field lines. This is just some of them, the ones that are represented in here. Now, if you think of the charge as being negative, and you bring a test charge, so if Q was actually the source in here, happened to be a negative charge, and you bring your test charge, instead of being pushed away, is going to be pulled toward it. And you do the same thing as before. So the field line are going to be sinking into the negative charge. Because again, 1 coulomb test charge is a positive charge. And if you put it next to a negative charge, it's going to be attracted to it, not repelled from it. It's going to be always attracted towards it, okay? Since it's attracted to it, then in this case, it's going to be the field lines are all going to merge into the source that is in this case negative. So the electric field emanates from the positive charge and terminates inside the negative one. I think that's a good enough extent to discuss this point in here. I mean, there is the so-called something like a dipole. Dipole is made up of a positive charge and a negative charge. So this is a dipole. So if you want to draw the field lines, well, the field line will come out of the positive and end in the negative on this line. And it's going to emanate from the positive and end in the negative. It's going to emanate from the positive and negative. So this is the dipole, the electrical dipole, like the antenna. This is a typical example, like an antenna. So again, it's going to come out. It's going to come out. And some of this line will leave from here and will terminate in here. And another one will leave in here. Leave, not come back. And come back in here. This one will leave this way and will terminate this way. So that is typical example in here of a electric field. So the electric field lines are really important because they tell you if you put a charge in here, a 1 coulomb charge, it's going to be repelled by the positive charge, but attracted by the negative charge. And the force is going to look like this, the resultant force. Okay, so they're important. Okay, the last concept that I need to introduce in here in this context is the electric field. And electric potential, I'm sorry. And the electric potential is one of the well-known concepts that you have encountered in your life, okay? This is the voltage on the power plug in your home, okay, or wherever you are. So that is the voltage that is necessary. So think about it. I have a battery. There's a positive and negative. Let's say, for example, a normal 1.5 volt battery. Okay, and at this point, if I take a light bulb, for example, so I'm going to draw a light bulb in here. I know we didn't do currents yet, but we're going to understand hopefully what this idea is because it's still dealing with charges. So I have an incandescent light bulb, okay. Or any device you want to imagine, okay? And let's put a switch in here. So we have a switch in here just to turn on the light on and off, okay? So that's what we're having. So if I close the switch, the current starts flowing. So what's going on in this case? So I have charges that electrons start to move this way, meaning that the current is moving this way, and it's going to go through the light bulb and the light bulb will light, okay? So in this case, what's going on in this case is I have a potential to drive charges, okay? So that is basically what's going on in here. And to drive charges, you make electricity, which is power, which is energy at the end of the day that is dissipated. So by definition, at least at this point in here, by definition, I'm going to use the symbol of the book for once, okay? The electric potential energy is equal to the charge that has been basically displaced by the voltage. So this is the voltage, okay? This is again the charge. So in a similar fashion, just like what we did earlier with the force and the electric field, when we said that the electric field is simply the force divided by charge. In this case, we're going to say the voltage is an energy divided by charge, okay? This is in joules, and this is in coulomb. So the unit for the voltage is in joule, the energy per coulomb. Actually, it has a name. The unit for the voltage is actually volt, in honor of Mr. Volta, who did the work in this area in here. He did actually build the first batteries, okay, chemical batteries. So in honor of Mr. Volta, again, it's either joule per coulomb, similar to Newton per coulomb, or volts. And that's what you hear all the time. And in battery, 1.5 volts. So when you go to the store and buy a battery, a AA battery, for example, all you're buying is the voltage, the potential to do work with it. Okay, sure enough, if you put it in a circuit, you could basically use it up till all of the juice in it is gone. Okay, I think this is good enough point to stop. I know the discussion is still not over, so next time when we meet, I'm going to continue on this from this point in here. And we're going to have more probably examples, especially in the context in light of the fact that you have an exam that is coming. So I'm going to stop right now here, and we're going to build on this one because this is important stuff. We're going to come back to circuits, so we're going to discuss more of these ideas more in detail. Hopefully we understand them better, and we'll build it from there. Thank you, guys. Please do not hesitate to send me messages if you guys have any questions or run into some difficulties or something. We want to make sure that you guys have all of the things you need to succeed in this class. Thank you.
Thanks, Professor.
Thank you.